Hello mathematicians, we're now going to have a look at what happens when expressions get a little bit more complex and our simple rule for differentiation can no longer be reasonably applied. So one of these cases is when we have what I call, what lots of people call, a function of a function. And the rule in this case is called the function of a function rule or the chain rule. So this occurs when we have y, which is some function of u, where u is in turn a function of x. Now that sounds really complicated, but if you just glance down at this first example here, this might illustrate it a little bit better. So we have y, which is a function of, and I'm going to call this thing here u. So we could think of y as u to the fourth. And u, the 3x plus 7, is of course in turn a function of x. So the chain rule says this, that dy dx is equal to dy du multiplied by du dx. So it's almost like ordinary fractions. You can imagine cancelling that out there, so it's all true. Dy dx equals dy dx. On the reference sheet it's written slightly differently, but same concept. So it's saying dy du equals f dashed of u, which is this symbol here. So dy du is the first differential of u, the capital F doesn't really make any difference, times du dx. So if we applied that method to this here, for example, if we didn't have an alternative method, we would have to use our present rule, we would have to say, I'm going to work out what 3x plus 7 to the fourth is by expanding it out and then apply my rule. But this lets us apply it in one fell swoop. So if y equals 3x plus 7 to the fourth and u equals 3x plus 7, then what we have is that dy dx is dy du, or the first differential of u, so that will be 4 times u cubed, multiplied by du dx. So I differentiate u with respect to x, which will give me 3. So 3 times 4u cubed is 12u cubed, and then I change my variable back to x, so that gives me 12 lots of 3x plus 7, all cubed. Now I am going to, as I said to you in class today, encourage you to think of this as a packet or a something. And we differentiate that something according to our base rule, and then we differentiate what's in the packet or in the something according to our base rule, and we multiply them together. So we just look at this and say it's 4 times the packet cubed times the differential of what's in the packet, which is 3, which of course gives us what we got up above, 12 times that. Now I might just look at this example here. So if this is what y is, then I'm encouraging you, I shouldn't have actually put that as an equals there, that should have been y dashed. I'm going to encourage you to say that y dashed, or more correctly dy dx, no, not more correctly, differently, that dy dx is, so 4 times my function to the 3 times the differential of my function in here. So when I differentiate that, that will be negative 4x. Now, if there's some point in tidying it up, we do it, and in this case, it's nice and easy to write 4 times minus 4x as minus 16x, and I get that. Now, the rules work in a similar fashion as we've seen for negative indices and for fractional indices. So if I look at this middle one, this is what y is, so y dashed is minus 3 times thing in the brackets, and now to the minus 4, multiplied by the differential of what's in the brackets, which is 10x. So tidying it up, that's minus 30x times 5x squared minus 2 to the minus 4. Down here, If this is what y is, we know that that is x squared minus 3 to the half. So y dashed, or dy dx, is going to equal a half times x squared minus 3 to the minus a half, multiplied by the differential of what's in here, which is 2x. So if I tidy that up, I've got a half. I've got my 2x up the top, so those 2's cancel, and I've got my x squared minus 3 down the bottom, courtesy of this negative, and a square root, courtesy of the half. So that's x on root x squared minus 3. Now I'm just going to make mention of these next two. They're both extension 1 topics, and this is just really mentioning them because they come up later in the course. We're not doing anything in depth on this at the moment, but we can cope with it at this stage. So a reminder that if y equals f of x, we know that the inverse function is written as x equals the inverse function of y, which we get by changing the place of the x and y basically, and then making y the subject again. The only lesson to learn out of this is that if we think of the chain rule up above and how the differentials multiplied as fractions, if we wrote dy dx times dx dy, that equals 1. So that gives us a relationship between dy dx and dx dy, that they're simply reciprocals. We'll do much more with that later on. Now I'll also mention something else we'll do a lot more with later on, and that's parametric differentiation. But first of all, just to mention what a parameter is. A parameter gives us an option of using a third variable which sort of controls our other variables. So in extension 1, the case that we will concentrate on with regard to the parameter is the parabola. There'll be a chapter called The Parabola in Parametric Representation. So if this is the equation of the parabola, now I know normally we'd write it as y equals x squared on 4, but this is how we do it later on. It can be written in parametric forms in terms of a parameter. There's nothing at all special about t. It could be any letter. So it's x equals 2t, y equals t squared. Now that means that as we vary t, that automatically varies the value of y and x in accordance with this equation up here. And in fact, for what it's worth, if we look at these equations, if we treated those as two equations, and I made, for example, t the subject of this equation, so t equals x on 2, and then put it into here, that would give me this equation without the parameter. So that's called eliminating the parameter. Now, if something is written in parametric form, we can find the slope of the curve and the tangent, dy dx, by dy dt times dt dx, according to the chain rule. Or, using the point from up above, what we could do, and as I said in class I'll probably encourage you to do, is to write dy dx as dy dt over dx dt. So we've got no need to take reciprocals. So if we look at an example, I'll just do B as our example here. If I wanted, for this particular curve, whatever it is, written in terms of the parameter, if I wanted the gradient of the curve, which is the gradient of the tangent, then I would write, then that's going to be dy dt over dx dt, so I'm using this format here. Now, if y is c on t, that's ct to the minus 1, so dy dt is minus ct to the minus 2, so that's minus c on t squared. Dx dt is just going to be c, and if I simplify that a little bit, this c will cancel out with that one, so I've got minus 1 on t squared. So I'm getting the slope of the curve in terms of this parameter. So when t equals minus 1, slope of the curve, again the slope of the tangent, when t equals minus 1, will be minus 1 on minus 1 all squared, which will work out to be minus 1. So the tangent, for what it's worth, has a slope of minus 1, angle of inclination of 135, all of those things that we already know. So have a go at these in 7E. I've started off with number 4. If you need some practice on the basic rules, go back and do some out of 1, 2 and 3. These are more about applying those rules.